Hey, sorry, welcome back. This is 14.4, and we're looking at some physics applications for Calc 3. Um, you may have, I guess we used to teach these things in Calc 2, but we sort of skip out on that now, but they are in Calc 3 here. Anyways, the formulas, you either get them in physics or I guess, I don't know where else you would get them, but um, anyways, the first one, we're talking about center of mass, and in particular, it's the balance point, right? So if you have like some sort of teeter totter, and maybe you have some sort of mass over here and then some sort of mass over here, the rotation on that triangle there, the teeter totter rotation, I guess, is dependent on two things: basically the distance of the mass away from the fulcrum and the amount of mass, right? So in your physics books, it's usually explained as the sum of mass times some sort of distance. And yeah, in our work, what we're looking at, instead of like objects on a teeter totter. So this is maybe like a simple physics intro to the physics class or something. Um, for us in calculus, the object that we want to find the balance point of will be some sort of sheet of maybe variable density, so it's thicker in some places than other places. And so this, for example, this region right here, and we want to figure out the balance point of this plate, I guess. So maybe, where can I put my finger so that I could balance this thing perfectly on my finger? Um, right, so you have your finger. I used to be able to draw a little bit, so here's my sketch of a finger. This is my hand, apparently. Um, yeah, it's not bad. And then I'm trying to balance that thing I just drew on that finger. So maybe I need a little bit more. Get rid of the top of the finger. You didn't know you were going to get some art today, but here we are. And yeah, so whatever the heck that thing was, I just have over there. So if I put my finger right there, the object will balance. Okay, so I kind of need to transcribe this idea from physics into these weird, uh, I guess the book's calling them lamina. Um, so how is that going to work? Well, instead of having like a fulcrum, you consider the axes as fulcrums. Okay, so you're going to have kind of a teeter totter on the x-axis and then a teeter totter on the y-axis, and you figure out the what they call the moments about those axes. So the moment about the x-axis is kind of the teeter-totterness over the x-axis, and it's dependent on the distance to the particular point, which would be an average in this case of the top and the bottom. Okay, so for instance, let's say this top curve is f of x and this bottom curve is g of x. The x value, so to speak, from the physics formula there is going to be, we'll say the center of mass about the x-axis is kind of the sum of the masses times, and the masses in this case would be kind of the area of that rectangle times its density. But anyways, it would be the mass times a y distance in this case, because you're talking about a distance from the x-axis. Okay, so it's kind of hard to imagine if I maybe laid the imagine me taking the y-axis as a pole, as like a, here's the y-axis, and I just laid it straight like this. Um, and maybe I don't know. Here's the x-axis as kind of a So you can kind of see how the y-axis would be like a teeter-totter on the x-axis. That would be kind of the same idea. So now this thing becomes kind of your fulcrum, and you're putting weight or these balls onto our onto this axis, and it's kind of rotating, you know, like this around this axis. Okay, and this distance here to now, and it's back in the original, we would have these distances to the balls, right, from the fulcrum, but now our fulcrum is the x-axis, so the distances are y distances. Okay, this distance right here from the x-axis is a y distance, and that's what you're going after with this this moment about the x-axis. Okay, and then likewise, you could pull the same business with the y-axis as kind of your fulcrum, right? And then you have a moment about the y-axis, right? So you imagine the x-axis is kind of a seesaw object. Kind of butchered that one, but then you have objects kind of on um, the so on the x-axis, and that's kind of teeter-tottering around. So in that case, that would be the moment about the y-axis, because you're kind of rotating on the y-axis, and for that value, it's an x distance, right? So the my in kind of terms of the physics version would be m the mass times x. Okay. So hopefully that kind of gives you a kind of an idea of what's going on here. Even if you have no idea and you're not a physics person, you could always just think of it as kind of a look up the formula kind of problem, right? So just make sure you're getting the right formulas. In particular, for us, the moment about the x-axis is going to be the kind of, you'll have a double integral for area, but then you need mass, so you have to include the mass formula, whatever that is. It's usually just a constant, but they can have variable mass. And then, of course, there's distances away from the x-axis, so you have to tack in a y there somewhere. Usually they put it in front of the row. So if you don't mind, I'm going to smoosh it in right there, and then dA, okay, over whatever region you're dealing with. So that's the moment about the x-axis. The moment about the y-axis then is just your kind of summing up the masses and the distances away from the y-axis will be given in terms of x. So then you'd have a row of x comma y dA over this region. To get the center of mass, so the center of mass they're going to give as x bar comma y bar. That's going to be equal to the moment about the x-axis divided by the mass, comma, the moment about the y-axis divided by the mass. And I didn't list the mass formula, but the mass formula is basically just a moment without the x or y distance. Okay, so the mass formula is basically just the area times the density. Right, so it would be area integral, double integral of the density function. Okay, and those are pretty much the first three formulas that you'll get in the book here. Everything else just comes down to your ability to do these integrals. So let's make sure I got the formulas. Sometimes I swap the terms. What, they're not giving you the formulas now? Jeez, man, really? Oh, here's the moment. There we go. Okay, so yeah, mx, yeah, y, and then, well, yeah, I did swap them. So it's my over, I always do that. Don't be like me, okay? Be better than me. So my and then mx. And it's really easy to do that. I was doing the homework the other day, and I know I did that on at least one of the problems. But let's see, what kind of problems do you have? Yeah, so find the mass and the center of mass of the lamina bounded by the graphs, the equations for the given density. So number 2, y equals square root x, y equals 0, x equals 9, and then our rho is variable ky. I think usually in the Calc 2 version, they always assume that the density is constant, and then you could do this with Calc 2. But for us, going to need Calc 3 thanks to that density issue. Anyways, usually you get the mass first. So the mass is just equal to the, and let's get a picture of this lamina. So y equals 0, of course, is just the x-axis, and then x equals 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 is this vertical line, and then y equals square root x is going to be this thing, where this point here is at 9, 3. So there's the region that we want. So I have the double integral of, so it's mass for us is going to be area times density. So I have this ky thing I have to worry about, and then, dA. I'll go the kind of traditional way that they do it is usually dy dx. So y, you're going to curve the curve as usual. So y equals 0 to y equals square root x, and then point the point, so 0 to 9. Okay, so 0 the square root x, and then 0 to 9. Okay, alrighty then. You could factor out the k, no big deal there, and then integrate with respect to y. So I got y squared over 2. I'm going to factor out the 1/2 and just have y squared from 0 to the square root x. And dx eventually. So I have k all over 2 integral. If you put in the square root of x and then square it, you just get x and then minus 0 dx. And then we're going to integrate that. So I have k x squared over 4 from 0 to 9. And of course that's just 81k all over 4 for the mass. And they want the mass in the problem. You can see I already put that in there. All right, now I need to get mx and my. I'm going to do my first because that is the first thing I need in my ordered pair. And it's better to get that kind of, if I put these on a test, I'd give you the formulas, and I expect to have these memorized, especially because some people haven't taken physics. So anyways, so the my, the moment about the y-axis is always going to be dependent on x values. So I'll have to, on top of the density function, I'm going to have to tack in an x, and then I go dy dx. So it's basically just the same integral with an x smushed in there. So then 0 to the square root x, 0 to the 9. And sure, double. So integrate this guy. I'm going to pull out the k. With respect to y, it'll be y squared over 2, so there's a half. And then I have xy squared evaluated from 0 to the square root x dx. Okay. So I need to evaluate that guy. K over 2 integral x times square root of x squared is x times x, which is x squared. And then minus 0 dx. So then I'm going to get k all over kx cubed all over 6, and I need to evaluate that from 0 to the 9. And then I'm getting, 729 maybe, something like that. 27 times 9. No, that's not 729. 27, 81. Gee willow. Really? Right? No, 9 cubed, Dave. 81 times 9. 729. I was first. 729 k all over 6. Clearly I can reduce that. I don't feel like it though. I don't trust myself anymore. Mx double integral 0 to the square root x, and then 0 to 9 of k y is a density, but then we have to tack on a y because we're thinking about distances from the x-axis. So it'll be y times y, which will be y squared. So let's just put y squared, shall we? dy dx. And that would be double integral, well, I can factor out the k. I'll have y cubed all over 3, so let's factor out the 3, the 1/3. And then I have to evaluate, and I have dx. Okay, great. So k all over 3 integral. Square root of x cubed will be x to the 3 halves, and then dx. And then that will be k all over 3. X to the 3 halves plus 2 halves is 5 halves times 2/5 from 0 to 9. That will be 2k all over 15 times 9 to the 5 halves. So that would be 3 to the 5th. 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 273. So 273. I can simplify that at least a little bit. Divide top and bottom by 3. That will be 5. This will be 81. So that will be 162 all over 5k. Okay, so then I need my my x bar and y bar. So x bar is going to be the 729k all over 6 divided by the mass. In other words, times the reciprocal of the mass, which is 4 all over 81k. 729 is 81 times 9, right? So this is 81 times 9. So I can remove these 81s. 4 over 6, same as 2 over 3. So that'll give me 18 all over 3, which of course is just 6. The k's cancel as well. Y bar then is going to be 162 all over 5k times 4 all over 81. I probably shouldn't have reduced that, right? So it's 81 times 2. Oh, there it is. Sweet. So the 81s are gone. The k's are gone. I just get 8/5 for my... So my center of mass will be at 6, 8/5. And in general, when you get your center of mass, that should be on the object somewhere. So if I got some negative numbers, no. That's not going to work unless there's like a hole in the object. I think for all of the answers they were on the lamina somewhere. Okay, so you can see 6 8/5 is, you know, it's in here somewhere. Okay, so again, if you're getting answers that are negative, you got it, or if you get an answer that's not on the object, you screwed up. You got to go back and do something else. Okay. Alrighty, more of the same, more of the same. Get some crazy answers in some of these questions. Is that a mass problem? Yeah, these are all mass. Oh, that one, look at that one. That's pretty nasty. So I wonder, I may have had to go to the 2 polar coordinates to pull that off. Let's try that one, so number 5, and see what the whole issue was. So y equals square root of 81 minus x squared, then y is less than or equal to x, and then rho is just a constant this time. It's very nice of them. So anyways, let's get a picture. So 81 minus x squared, that thing right there's a circle with radius 9, right? 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there. Okay, y greater than or equal to 0. So that's the x-axis, and then less than y equals x. So the region we're after is this wedge region here. Okay, that's the thing we're trying to find the balance point for. So the integral for mass, then as usual, double integral of rho, which is a constant, so I can pull it out of the integral altogether. And then dy dx. It's almost like you want to go Just take 1/8 times the area of that circle. I bet that would work. What is that circle? Pi r squared. So 81 pi, then times the constant and divide it by 1, 2, 3, 4, 5, 6. There's 8 of them, right? So divide by 8. Oh yeah, and you can see that's the answer. So a lot of these you can just use common sense to kind of pick out the answer if you don't feel like doing an integral. But you're going to have to do the integral anyway, so you might as well get this amped up and see what's wrong with it if I have to go to polar coordinates or something. Did I do polar coordinates yet? Polar coordinate conversion? Yeah, I just haven't done it in triple integrals. Okay, yeah, so you may have to go polar here. Anyways, I'm going from yeah, so it would be kind of a nightmare because you would have two kind of regions. You'd have two integrals you'd have to deal with in order to get it to work out. So instead of writing it out in all of its weird glory, let's just write it like this at first, and then convert the polar. Right. So we have k times the double integral of r dr d theta. And in this case, I'm going from r equals 0 to r equals 9, and then at 0 to pi over 4. Right. So go ahead and get that job done. So the integral of r with respect to r squared over 2, pull out the 2. Yeah, I already put it over 2. Give me the eraser. So r squared from 0 to 9 d theta. So this will be k over 2 integral 81 minus 0 d theta. So I have 81k all over 2 times theta from 0 to the pi over 4. And of course you get the same answer that we thought we would get. So 81k all over 8 times pi for mass. Okay, so let's see what the heck the other issue was then. For a moment about y, you're talking about x distances. You can factor out the k. So it's in polar coordinates, x is r cosine theta, but then you have another r from the r dr d theta. So it's r squared dr d theta. And same bounds, so 0 to 9, and then 0 to pi over 4. So it's k integral. So the first one would give you a 3 popping out, but it would be r cubed cosine theta d theta. I have to evaluate this thing from 0 to 9. 9 cubed, 279, but divided by 3. I'm just going to leave it as 279k all over 3. Like I can't do 93, right? Something like that. Then I have an integral of cosine of theta d theta. So that would be 279k all over 3 times sine of theta from 0 to pi over 4. So it's just going to be 279k over 3 times pi over 4. So 279 sine of pi over 4. Right? Over 3. Sine of pi over 4 is root 2 over 2. So you end up with a root 2 over 2. And then that would be 279 root 2 all over 6. And the moment about the x-axis then, it's the same integral except instead of having cosine you have sine, right? So k r squared sine theta dr d theta. So I should be able to just cheat a little bit with using the last integral. So I'd have 279k all over 3. And then instead of having sine, you'll have negative cosine theta of pi over 4 to 0. So this would be negative 279 root 2 all over 6, which totally doesn't seem right because you have to then, okay, so I see what the issue is. Then minus because cosine of 0 is 1, whereas sine of 0 is 0. So let's rewrite this. 279k all over 3 times negative root 2 over 2 minus negative 1, right? Because it's minus negative cosine, so it would be plus 1. Okay. All right. Then you have your centers of mass. So the x part is the 279 root 2 all over 6 times 81k, the reciprocal of that, 8 all over 81k, and I lost my k value. No, I didn't. It's in there. It's right here. Oh, I lost it on this one. So there's a k here. Okay. I don't know if I ever had it. Yeah, it was in there. I just lost it. Alrighty then. So what is this guy? 279. What is that? It's 3 times 81, isn't it? No, it's not. It's 9 times 81. So the 81s cancel. 8 over 6 is the same as 4 over 3. And then 9 over 3 is the same as 3 over 1. So it looks like I'm getting 12 square root 2. Yeah, and I lost my pi. There's an 81 pi in there, all over pi. Y bar then is this big ugly 279k all over 3 times the negative square root of 2 all over 2 plus 1 times 8 all over 81 pi k. So the k's cancel. Again, 279 is the same as 9 times 81. So get rid of the 81s. 3 into 9 is 3. So it's going to give you 24 over pi times negative root 2 over 2 plus 1. Yeah, it's just kind of real easy to make little mistakes. So just be careful. And I'm sure if you're tired, oh my gosh, it's just going to be worse. So 12 root 2 over pi, comma, try to get your sleep, get 8 hours, good 8 hours a day. Negative root 2 over 2 plus 1. Okay, and then we move into center, the second moments, I guess. So let's see what those are. Right. All right, so this is all center of mass junk, center of mass junk, center of mass. Moments of inertia. So this is the mass's resistance to rotation about an axis. Okay, so you're thinking about like pushing a door open. The door swings on an axis, right? It swings on its hinges, which you could think of the hinges as like a y-axis, I guess. And the heaviness of the door. So if you've ever been to like a nuclear missile silo, the blast doors in there, they have to be like scientifically calibrated to be for them to be capable of being opened and closed, because they're like, you know, really heavy doors, but you could still push them open and close. But anyways, the door's resistance to that is kind of what we're figuring out right here. It's called the moment of inertia, or the rotational inertia. Okay, so I think the book calls it the second moment. They called it the moment of inertia as well. So let me put moment of inertia. And the formula for moment of inertia from basic physics, like above, we had the sum of the masses times distances away from the fulcrum. Now it's going to be the sum of the masses times the square of the distances from the fulcrum. So now in calc, the picture, we're dealing with some sort of region given by some curves. And with regards to the x-axis, again, we're thinking about a distance away in terms of y. Okay, so you're going to have two moments. You'll have and you see the formulas there to the right. You have the I sub x moment, which will be a mass times this x squared. So for the mass, it's the density times area. So we could have a variable density formula and then dA over this region. The other version then is about distance away from the y-axis, which will be given in terms of x. Whoops, I lost my y for the, there should be a y in here. Keep doing that, smush it in there. So this one will be having an x in front of the row, dA over this region R. Let me rewrite that. That just looks awful. There's a y right here, okay. All right. Again, it comes down to plug and chug. There's also a polar distance, I sub 0, which they're after every once in a while, which you could just find from the sums of these two. This should be y squared and this should be x squared. I apologize. I don't know what's wrong with me. But anyways, this polar moment is going to be x squared plus y squared. So usually what you do is just find I, x, I, y, and to get the polar one, you just add them together. Okay. All right. So anyways, again, if you know nothing about physics, you can just think of it in terms of plug and chug. You could derive it from the kinetic energy formula and all that jazz if you're super interested and super motivated. Well, I'm not going to do that. I'll leave that to your physics teacher. There's also this radius of gyration. We'll look at that again once we get to triple integrals. And again, if you can just think of it in terms of plug and chugs. Okay. So let's see what the homework has for us. I don't think I put a lot of them in here, but in some cases you can use a computer to satisfy these, make sure they work, but let's just look at the last two, I guess. So in the last two, I'm after gyration. Maybe I should give you the formula for gyration, right? So these were the moments of inertia. And then the gyration points, they're kind, you can kind of think of them kind of like, I don't want to say it, but a center of mass, because the formula is similar, but there's a square root involved. I sub y over m, where m is mass. I should write mass. Y double bar. Y double bar is going to be Ix all over m for mass, but it has to do with rotation. It's not the center of, it's not a balance point thing. Okay. All right. Let's take a look then at number 7. So we're going to need the mass. We're going to need these second moments. So first, let's get the mass. And rather than screwing around with a double integral, because it doesn't seem it's really necessary, we can just, wow, this is really simple. This is going to be very simple. So 1/2 base times height, right? So 1/2 base is b times height is h. And then x, well, there's no calculus involved. I want to do a calculus problem, right? Well, so you're not even going to have to. Well, that's fine and dandy. Okay, so anyways, x double bar, they give you I sub y. It's so you have the square root of 1/12 b cubed h all over 1/2 bh. So that's going to be, doing reciprocals, 1/6 times b squared, and that'll just be b over square root 6. Y double bar, then again they give you I sub x, which is 1/12 bh cubed all over the 1/2 bh. That'll be the square root of 1/6 times h squared, which will be h over square root 6. And there you have it. Okay, great. Let's look at number 8, and I can show you how to put these things into a computer. All right, so number 8, and let's make this the video quiz for this section. So this is in video quiz set number 7. This will be the 4th problem in there. And I'm just marking it down in my notes. Number 8 in WebAssign. Okay, so let's try it. I'm going to figure out what the region is. So y equals 0 to y equals b, x equals 0, x equals a, rho equals ky. Right, so the mass, I need that, is going to be, well, I got to figure out what the region is, sorry. So the region, y equals 0 is the x-axis to y equals b is right here. X equals 0 is the y-axis to x equals a, which is right here. Okay, so the mass is, you don't need a double integral for this, it's just, well, yeah, I guess you would, because there's that pesky y in the rho formula. Okay, so sorry about that. I guess the double integral, I don't even think you need a computer for this. 0 to a, 0 to b of ky. And then I guess the way I did it was dx dy. Sorry. Okay, so this is going to be the integral of kxy from 0 to a dy. So it's going to be the integral of, let's factor out the ka, and then you're kind of stuck with this y in here, dy, and then that's going to be ka all over 2y squared from 0 to b. That will be kab squared all over 2 for your mass. Okay. Let's see how I would do that in an integral though. So usually I use Wolfram. I don't do Symbolab or whatever those other ones are. I like this one because it's more like coding. Makes me feel like I'm doing something special, like driving a stick shift, you know. So anyways, int and then int of int, those are integrals of k star y, comma, and I'm going to put x first, x equals 0 to b, comma, y equals 0 to a, and then I'll end all that off, and then end that off, and hit enter, and the software should tell you what you're doing. Are you serious? All right, let's factor out the k and see if it can handle that. It's telling me the answer is Kentucky. I don't know why it's giving me such trouble. Oh, I put in the wrong parentheses there. I bet it'll be happier now. I probably have too many parentheses. There we go. Sorry about that. So there's the code. You know, you just put your function in there. Yeah, a squared. Oh, right over. I couldn't. Oh, I did. X goes from 0 to a. I was going to switch those. Y, make that y, make the other one x. Okay, so ab squared over 2. Then, of course, the moment, second moment about the y-axis, I sub y, is with the x squared. So I need to put an x squared in here. And this will be, don't forget your k value. Do not buy software. Okay, do not buy Wolfram. Yeah, even though it's going to try to sell you, I would not. No, do not buy anything. Okay, do not buy any software. Don't be crazy. So I accidentally erased everything because it was trying to sell me something. Int of what did we say? The first one was x squared times There's already a y in there, and then I want to go y equals 0 to b, and then parentheses x equals 0 to a. So this will be a cubed b squared all over 6k. And then I need the y squared version for I sub x. So I should just be able to hit enter and be done with it. It's saying ab to the 4th over 4 times k, which doesn't seem right. Let's see if those are right. Yeah, I sub x is right. ab to the 4th over 4 k, a cubed b squared k. I sub 0 is just, if you notice, it's just the sum of those two. So I sub 0 will just be a cubed b squared all over 6k plus ab to the 4th all over 4k. And then I need my gyrations. So x bar bar is going to be the square root. Is it I sub x or I sub y? It's I sub y. So we have a cubed b squared times 1/6k all over 1. Where the heck is the mass? It's right above there. 1/2 ab squared k. So that would be 2/6, which is 1/3, then a squared. So it's going to be a all over the square root of 3. Y double bar. It's sort of the same procedure here. We have 1/4 ab to the 4th k all over 1/2 ab squared k. So it'd just be square root of 1/2 b squared. So that's going to give you a b over root 2. And of course, those are the answers. So yeah, you can, when we get in the physics stuff, you can use the computers like Wolfram to do your integrals, because odds are I'm not going to put hardcore physics problems on your test. Okay, because like I had never taken physics. I was more into, believe it or not, philosophy, and some arguments. So okay, so very good. We'll leave it at that. Thank you for watching as usual, and I'll see you next time.